Okay. Hi, everyone. My name is SaraSADRI, and my talk is about water resources optimization and irrigation advisory based on farm-level remote sensing and crop water demand. Before I begin, I wish to acknowledge my collaborators and thank them for their help so far. And with that, I will start my presentation. The outline is pretty straightforward. I start with a background and describing the problem, setting up the goal, presenting you with some methodology and results, and moving to discussion and next steps. So a little bit of background here about how water and food security are intertwined. There has been three agricultural revolutions. The first one was from 1900 to 1930, which was with the increase of mechanized agriculture, a farmer was producing enough food to feed about 26 people. From 1930 to 1990 is called Green Revolution. With the new methods of crops genetics, genetic modification, a farmer was feeding 155 people. We are now in the third wave of agricultural revolution, which is expected by 2050, the global population will reach about 9.6 billion. And if you think about it, the food production must also effectively double from current levels in order to feed every mouth. So there is a more pressure on the farmer to produce more without change of the farmer's acreage or water availability. So we have to find new ways of optimizing crop moisture deficit and water stress distribution at farm level through the use of the technological advancement. And that information also needs to be available to the farmer in real time in order to empower the farmer in making better management decisions. So with that, on a question underlying this study is that can a farm manager be advised about the amount and the spatial distribution of water deficit in the farm for the following week? And that would be for optimizing crop yield. So the goal based on that is to develop a tool to monitor and forecast with 7-day lead time with a subfield resolution at 70-meter resolution, crop water stress, which is ET over ET0, and the amount of additional required water supply, which FAO calls it irrigation needed, in order to compensate for the crop moisture deficit. So how would we do that? The methodology uses the qualities of near real-time remote sensing data representing both atmospheric and soil properties coupled with the information that the farmer provides, as well as water balance and machine learning techniques to generate high-resolution spatial map of next week crop water stress and irrigation needed, as well as the historic graphs and data for the farm. One unique aspect of this project is that it takes advantage of the information that the farmer provides to match crop phenology, crop type, and FAO's guideline with the soil moisture depths needed in the calculations. Now, the study area is the Canadian Prairies ecozone, or CPE, in central Canada, highlighted here in beige color. Canadian Prairies ecozone is the breadbasket of Canada, with 80% of farmland being there. Nevertheless, it is the area very vulnerable to recurring droughts and waterlogged conditions that cause millions and billions of damages on the Canadian economy. I chose six sites from Saskatchewan and Manitoba, 4 from Saskatchewan, 2 from Manitoba, naming them S1 to S6. These are all rain-fit farms. The average farm is 200 hectares, and I chose them based on the availability of the SMAP core in-situ sites and RISMA in-situ sites. That is the location, and I mostly represent the S1 data here in this talk. So I'm showing the remote sensing and global data I'm using along with information about their period of availability, spatial and temporal resolution. Except for elevation here, all the records are available in near real time and can be accessed and downloaded regularly. Precipitation is also an exception because the forecasting data for precipitation is available regularly. Here we can find more information that are detailed about the 6 study farms S1 to S6. The crops planted for each farm rotated annually. They are mostly canola and spring wheat, but we are also seeing soybeans, oats, and barley and peas and lentils. The total precipitation from April 1 to October 31st, which is the agricultural period, is the major part of annual precipitation, and potential evapotranspiration is obtained from the National Atlas of Canada at this stage at least, and the growing season aridity index for each farm is calculated in the last column. This growing season aridity index is very important because, excuse me, this growing season aridity index is important because it represents biogeographical distribution of vegetation. In addition, long-term forecasts of aridity index are more useful than daily weather, and it is especially used for predicting crop yield. Here I show the time series of weekly data for farm S1 in the period of 2015 to 2019. The top plot is showing the average soil moisture and root zone soil moisture and total weekly precipitation. Pink bars are a week apart and cover the agricultural period of each year. We see that in general for farm S1, root zone soil moisture is consistently above surface soil moisture, which is a useful thing to know for a specific farm, especially when the crop is in the maturity stages. The lower plot shows the sum of ET over ET and ET0 in red and green series. On the right axis, we have the ET over ET0 or stress index in blue series. The closer this, except for the winter time that we see that the ground is frozen, the closer ET over ET0 to 1, the less water is stressed for the crop. So the crops are generally stressed throughout agricultural year, but more so during the initial crop development and late season stages. Now some results, or some more results, I would say. I wanted to study the distribution of key variables on the farm given the remotely sensed overpass points around the farm. There are several spatial interpolation techniques, but here I use the common method of inverse distance weighted approach, or IDW, which uses a nearest neighbor approach. And compared to the normal averaging, the IDW points are, in IDW, points that are further away get less weight in predicting a value at a location. So here we show the downloaded, the downscaled version of the average ET, ET0, ET over ET0 soil moisture, root zone soil moisture, and the topography. All of these 5 ones are for the period of 2015 to 2020. There are all in 70-meter resolution in farm S1. For each variable and for every 70-meter grid in farm S1, the nearest satellite data covering the 4 corners or 4 sides of the farm were found, reprojected, and rescaled. So overall, except for the topography, the average pattern of changes of variables on farm S1 are not significant. But keep in mind, this is only one case study, and the goal is to have a methodology in place for various farms and scenarios. But for this particular farm, we can tell at least that the northeast is the lowest elevation and increases as we move to southwest part of the farm. The same patterns can be also seen in ET and ET0. Northeast is the part with the highest ET. The ET over ET0 can tell us give us more general picture of the part of the farm that can be more water stressed in general. In this case, overall, this southwest with the higher elevation is more water stressed, but more tests are needed to make a generalized statement about the causation of such correlations at the farm level. So the next question is, what is the information that a farmer can get access to in real time? There is an example of that here. Let's assume today is July 1st, 2019. And in this date is corresponding to the mid-season or 3rd stage of development of the crop, meaning that at this point, roots are fully developed and roots on soil moisture matters. Therefore, roots on soil moisture is in the calculation and surface soil moisture isn't. So we are assuming that the current day is July 1st, 2019 again, and the information includes that the information that we have is the precipitation for the last week and next week, past week root zone soil moisture, as well as ET and ET0. We use this information and this exact 14 days from the previous years all the way back to 2015 to predict the ET and ET0 for the next week using random forest, which is a machine learning technique. Then the total ET can be deducted from the next week's total precipitation, and the crop water deficit, which is 7.4 millimeter for the next week, can be distributed throughout the next week in a way that also adjusted for the amount of precipitation. Next is that how is this water deficit of 7.4 millimeters distributed across the field? Is it all unified, or some parts need more water and some parts need less? So I use the random forest again, but in this case for training, I use the farm 70 meters grid data of past year's 14-day window around today, plus past 7 days this year. And the output is the irrigation needed on each grid, which is produced from deducting which is produced by random forest, but the training part of it is deducting the precipitation from the ET. As I mentioned, since the crop is in mid-season, we are using only root zone soil moisture here. And the output is water deficit values in 70-meter resolution over the farm S1 shown here. Some parts seem less water deficit than overall 7.4 millimeter per week. So to be more exact is that when the farm needs irrigation or excess water supply, we can save water by having this knowledge of not all part of the farm need the same amount of water. So some validation efforts here are done by comparing the SMAP core validation sites with the SMAP overpass points around the farm, as well as the interpolated grid that these in-situ sites are right on. So the results are shown here at the table below. You can see that there are 3 core validation sites, naming here as top left or TL, bottom left or BL, and bottom right or BR. And they are repeated here. So we have the distance of each of these points to the SMAP overpass point, as well as the root mean square error values. In the last column, we have the root mean square value between the interpolated data and the in-situ data. The in-situ data are for 2015 to 2016. 2 things that were obtained as a result from this table is that, first of all, the distance of the SMAP overpass site to core validation site did not cause a difference in the root mean square error. So distance kind of doesn't matter in this case. And the second thing that we could calculate is that the result of the interpolated data using IDW in terms of RMSE with in-situ data and that from SMAP data is very similar. It's not that different. So the IDW is a good method to use in this case. So that's the other result that we have. So let's have some discussion here. We can do more validation on, of course, that we could do the validation for each of the covariates, and the calculate crop water stress can be done. The IDW method that I used for downscaling is a purely statistical method, so it does not consider physical processes. However, most of alternative LSMs also don't care about the water-carbon energy interaction, and they cannot also be run in near real time, which is a very important feature of this tool. The other predictable variables that can be predicted reliably for the next week, such as wind speed, snow in terms of centimeter, and temperature, can also be integrated in future estimation of ET. And currently I'm using only precipitation, but soon it should be replaced by effective precipitation. So lots of more work to do, and coupling crop yield and fertilizer, for example, with this crop water stress tool, using NDVI and image processing for better estimation of crop water, for better estimation of crop development, as well as using empirical orthogonal function for understanding the variability of these variables across the field. We can use or transfer this tool into an app for a farmer to get feedback from the farmer, and also understand that really those remote sensing data help us in better understanding crop water stress, yield, and monitoring the profits in a farm economy. Last but not least, wetlands are a fact in Canadian Prairies ecozones, and future research should exclude these from the farm plans or outputs, so that it looks more accurate, also for removal of any biases. With that, I would like to thank you for listening. Also, if you have, and I want to invite you, if you have any questions and interesting points or discussions or advice, please do not hesitate to reach me. So I look forward to your feedback. Thank you and have a nice day.